Okay, let us move on. We have started a new chapter, which is about porous materials. And the first class of porous materials we discussed were the zeolites. The zeolites are a form of crystalline microporous materials. And then we have begun to talk about periodic mesoporous materials. So these materials have crystalline pores, but they do not necessarily have crystalline channel walls. And the first class of periodic mesoporous materials we discussed were the periodic mesoporous silicas. And then the last point was how can we actually incorporate organic functionality in these periodic mesoporous silicas. And we discussed basically two approaches. So we can either use the cyanoid groups on the pore surfaces and graft functional groups on these pore surfaces via the cyanoid groups, or we use silsesquioxane precursors that have organic groups bound to silicon via silicon carbon bonds. And the last type of silsesquioxanes we discussed were ring molecules, such as this three-membered ring here. And we have shown that by using such a ring structure, you can double the number of organic functionalities in this material, just because within a ring structure, the silicon is not only bonded to one bridging group, but it's actually bonded to two bridging groups. So which properties can you actually tune this way? And one property you can tune is the dielectric constant of the material. And the dielectric constant material is important for electronics applications. So on a microchip, you have the problem that you have to electrically insulate it, the electrically conducting components from the electrically insulating components. For that, you need an insulator with a low dielectric constant. And this problem becomes the more significant, the smaller the device feature sizes are on your microchip, because the electrically conducting parts come closer and closer together. So here on this slide, you see how the organic group content can actually influence the dielectric constant properties of a material. So you see here actually the dielectric constant K versus the molar fraction F of periodic mesoporous organosilicas, which are co-assembled from a mixture of the three-ring precursor and a completely inorganic precursor. So the higher the molar fraction F for the three-ring molecule, the more organic groups you have within your material present. So you see here that you see clearly here that the dielectric constant is a function of that molar fraction F. And you can also see that the final dielectric constant that you can achieve depends on at which temperature you calcine your material to remove your surfactant. So at 300 degrees Celsius, the final dielectric constant from the material that is only made of this three-membered ring is still relatively high. It's about 2.5. But at 400 degrees Celsius, it is significantly lower. It is actually 2.0. So how can you explain this behavior? You can explain it through a process which is can be called a self-hydrophobization process. So when you investigate the thermal properties of this material more closely, then you can see by thermogravimetry investigations that there is no loss of organic groups up to a temperature of 500 degrees Celsius, and there is no change of order and size of mesopores up to 500 degrees Celsius. But the silicon-carbon bond cleaves already at a temperature of 300 degrees Celsius. However, the silicon-carbon bonds do not cleave completely, they only cleave partially. So you can actually show by solid state NMR spectroscopic studies that you have a so-called D to T site transformation between 400 and 500 degree Celsius that eliminates cyanoid groups. So here is actually how this process happens. So you see here two 3-ring molecules, and you see that one carries a cyanoid group, and that cyanoid group can now interact with a silicon in a CH3 group. So that can actually form a silicon-oxygen-silicon bridge, and it can also form a methyl group. Okay, and these methyl groups are significantly less polarizable than CH2 groups. In addition to that, you have eliminated these polar cyanoid groups. And by these two effects in combination, you can explain that at 400 degrees Celsius, you see a lower dielectric constant than at 300 degrees Celsius, because at 300 degrees Celsius, still a relatively large amount of cyanoid groups are present, while above that temperature, around 400 to 500 degrees Celsius, we get a self-hydrophobization effect in which these cyanoid groups are eliminated to form less polar silicon-oxygen-silicon bridges, and methyl groups are forming. All right, so this chemistry is even more versatile because the CH2 groups that bridge that ring have the property to be slightly acidic. So you can actually lithiate them with a strongly basic agent such as T-butyl lithium. And then subsequently, you can substitute that lithium using an electrophile. So for example, ethyl iodide, you can also add just halogens to that lithiated ring, and then you have further opportunities to functionalize these rings. And also these modified rings can then be self-assembled using a surfactant template to produce a periodic mesoporous silicon. So this way you can not only introduce relatively passive functionalities such as CH2 groups, you can also include more active functionalities. You can even extend this concept to link rings together. So if we use di-functionalized alkyl halide, then together with T-butyl lithium, we can link two of these 3 rings together. And also these now very large molecules can be used as single source precursors for a periodic mesoporous silica material. So an interesting aspect here is also that the R group that can be incorporated can be an alkyl group which is longer than just 2 carbon atoms. Okay, I told you previously that when you want to place a propyl group into a standard sulfesquioxane precursor, the self-assembly doesn't work anymore. But when you place the same propylene group in between these 2 rings, then you can still self-assemble a periodic mesoporous structure from the respective precursor. And you can explain this by the fact that these rings in itself are rigid and they provide more connecting points for the framework formation. So they actually stabilize the framework mechanically so that the framework can accept more flexible organic groups, such as propylene groups. Okay, so this idea can be further extended to form periodic mesoporous silicas from dendritic building units. So a dendrimer is a particular type of a polymer. It's a kind of spherical polymer which has a monodisperse molecular weight distribution, and it can be prepared from a dendrimer core, so which then arms are added in one or more consecutive reaction steps. So when you actually functionalize such a dendrimer with triethoxyl groups, then you have basically a sphere, okay, that can adopt nanoscopic size, which is functionalized with ethoxyl groups. And then this spherical molecule can again act as a suitable precursor for a periodic mesoporous material. Okay, so in the most simple case, such a dendrimer would have a silicon core. It would have four organic bridges around the silicon core, and then it would be functionalized by triethoxyl groups, which would be bonded to the group R. So this would be a so-called first generation dendrimer because it has only one layer of spheres surrounding the core. How can you make such a dendrimer? This is actually shown here. So for instance, you can start with tetravinylsilane, as shown here, and you can do a so-called hydrosilylation in the presence of a platinum precursor. And basically, the silicon hydrogen bond adds to the carbon-carbon double bond, and then you produce a molecule which has a trichlorosil head group. Okay, and then you can just hydrolyze these chloro groups. Sorry, not hydrolyze, but ethanolyze with ethanol. And then you have ethoxic groups attached to the silicon. And that then would be a suitable precursor for a periodic mesoporous material. Okay, so you can, again, either acid or base catalyzed in the presence of a surfactant produce a periodic mesoporous silica from it. All right, then here you actually see a second generation dendrimer, which has also been shown to self-assemble. So in this case, you have a core, okay? And then you have here, you see here, first generation shell, okay, of 4 other silicon atoms, okay? And then around that, we have a second generation silicon shell, okay? Now, also this molecule can be used as a single source precursor for periodic mesoporous silica material, even though this molecule is already almost 2 nanometers in diameter itself. Okay, you can further vary the scheme. You can also have a more complex core. So in this case, you have a core made of 2 silicon atoms bridged by a CH2 group, and then you have these ethyl triethoxysilane first shells bonded to the core, of which there are overall now 1, 2, 3, 4, 5, 6. So this would be another first generation dendrimer, and also this kind of dendrimer can be assembled into a periodic mesoporous silica, which you can then rename to be periodic mesoporous dendrosilica. All right, now we can expand this kind of chemistry even further. And I have to use actually now a new share. To what is called periodic mesoporous buckyball silicas. So you can also use fullerene as a core and then functionalize such a fullerene with tetraethoxycyl groups. So for instance, you can react the fullerene in a hydroamination reaction using this aminopropyl triethoxysilane here, and this way assemble a siliceous shell around that fullerene core. Okay, and then you can use the respective molecule as single source precursor for periodic mesoporous silicas. Okay, but it has been found that in order to assemble this, you will need again a co-assembly with tetraethoxysilane or tetramethoxysilane. The reason for this is that the number of triethoxycyl functionalities here around the buckyball isn't large enough, and also these propyl groups are relatively flexible. So we overall do not have here enough triethoxycyl groups surrounding that buckyball in order to enable it to act as a single source precursor. All right, another extension of this concept is to use silicon nanoparticles as building blocks for PMOs. So you can make silicon nanoparticles that has a few meter, which is a few nanometers in diameter. And these particles have the property that they have silynyl groups on the surface. And then you can use the reactivity of these silynyl groups in order to do a hydrosilylation reaction with a vinyl triethoxysilane molecule at 170 degrees Celsius. And this again gives a dense layer of triethoxycyl groups around the silicon core. Okay, and we can use these functionalized silicon nanoparticles then again as precursors for a periodic mesoporous organosilica material in conjunction with mesoscopic templates such as settled trimethyl ammonium bromide, for example. All right, so here's just how you can actually make these silicon nanoparticles. So they can be made by thermally induced disproportionation reaction. So trichlorosilane and water reacts to a material with the composition HSiO 1.5, which can then further react to SiO2 and nanocrystalline silicon. Okay, so this reaction step here is a disproportionation reaction. So part of that silicon is reduced to elemental silicon, and part of it is oxidized to silicon in the oxidation state +4. So this gives a mixture, so you can then remove the SiO2 part with HF and ethanol, and the silicon nanocrystals are then available for follow-up reactions. All right. So now we have talked about siliceous materials a lot, which are mesoporous. So can we also make mesoporous materials of other oxides? And the answer is yes. So this aqueous templated sub-assembly process also extends to many other metal oxides, but it's often technically more difficult to make these kinds of mesoporous metal oxides because they have a different, well, hydrolysis and condensation behavior. So we have to adjust the precursor, okay, to the specific hydrolysis and polycondensation behavior of the respective metal oxide. Okay, so for example, if you want to make mesoporous titanium dioxide, then this is possible. But in this case, we would use titanium isopropoxide as the precursor. Okay, not ethoxide, but isopropoxide. So why do we do this? This is because the titanium ethoxide would hydrolyze just too quickly. So we actually can avoid this by placing bulkier isopropoxy groups around this titanium. Then the hydrolysis process is slowed down for kinetic reasons and occurs then at a rate that allows us for a successful self-assembly process into mesostructured titanium dioxide. So the same goes also for other metals. So each metal oxide is its own system, and the reaction conditions have to be adjusted. Okay, the choice of precursor is certainly important, but also, of course, the other reaction conditions. For example, the acid or the base concentration also determines the hydrolysis and condensation rate of a metal oxide. The temperature does. So there's a lot of trial and error necessary to find the right reaction conditions for successful self-assembly. But after enough tinkering with these reaction conditions, one can these days, meanwhile, assemble almost any metal oxide in a mesostructured or mesoporous form. So here, just a few other examples of tantalum, aluminum, tin, tungsten, all have been successfully self-assembled into mesoporous oxides. Okay. So now can this concept also extend it from oxides to non-oxides, and even this works. So, for instance, one can make mesoporous carbons through that process as well. When you actually use hydrophilic precursors, such as resorcinol and formaldehyde, and polycondense these precursor molecules in the presence of a tri-block copolyether. Why does that work? Because the tri-block copolyether has a hydrophilic shell, and these molecules here are also fairly hydrophilic. So they preferentially go into the hydrophilic shell of the micelles, where they can react then and form a formaldehyde resin, okay, which is three-dimensional. Okay, it's also having sufficient rigidity in order to remove the template removal process, upon which it then carbonizes. Okay, so when you just heat your composite material made of that mesostructured formaldehyde resin and your template, then your template actually disintegrates into small molecular fragments, okay, while your formaldehyde resin actually carbonizes. Okay, when it carbonizes, because of its different chemical composition, in this formaldehyde resin we have mainly sp2 hybridized carbon, while in the template we have sp3 hybridized carbon. which have very different thermal behavior. So during heating, the template leaves and the pore walls decarbonize, and the result is a periodic mesoporous carbon. And again, you have the opportunity to produce periodic mesocarbons with different pore structures depending on which template exactly you are using. Okay, so let's have a closer look at the polymerization mechanism that makes the formaldehyde resin form. So we have formaldehyde in the system, which is aqueous, okay? And the formaldehyde can formally hydrolyze to form this species here. And that species here can then eliminate water and become protonated to form this cation over here. Let's go to this cation over here. We have then this cation that can react with the resorcinol here, okay? Because that resorcinol is an electron-rich aromatic, okay? Therefore, it's actually prone to electrophilic attack from this cation here, okay? So after removal of a proton, we have now generated this species here, okay? So this species here in an acid environment can again be protonated here in this position, and the respective cation here can then lose water and make this also quinone methite. Okay, where we have here an oxo group and here a CH2 group. Okay, at the same time, this species here, which is again shown here, there's actually a small typo because here the 2 is missing, can react with this species here, resorcinol, to form this species here. And you see that in this species now, 2 aromatic groups are linked together via CH2 group. Okay, so essentially we have here an electrophilic attack of this cation here, the position of that carbon on the aromatic ring over there. In this way, we form a carbon-carbon bond, and they will eliminate water. Okay. Also, this quinone methite can react with resorcinol. Okay. In a similar fashion to produce the same molecule here. And then the process just repeats itself. So this formed molecule can again become a reactant together with formaldehyde, and we have, well, a polymer growing in which benzene rings are interlinked with CH2 groups to form a 3-dimensional polymer. Okay, and that polymer then relatively easily carbonizes at very high temperature. All right, so carbons are not the only kind of materials that are non-oxidic and can be assembled into a periodic mesostructured form. One can also expand this concept to, for example, sulfides. But when you go to sulfides that are potentially prone to hydrolysis, you have to switch from an aqueous solvent to a non-aqueous solvent. Okay, but it also has to be a solvent in which you can still form micellar structures. Okay, that means that your solvent still has to be a very polar solvent. So a very good choice is formamide. That's one of the very few organic polar solvents which are polar enough to allow micelle formation. But in formamide, you can produce something like a mesostructured germanium sulfide For example, you can start out with this germanium cluster here, which is an adamantane structure. Here you see each germanium is surrounded by 4 sulfide anions, whereby these ones here, they are bridging 2 germanium atoms, whereas these 1, 2, 3, 4 ones, they are terminal and have a negative charge. So you can dissolve tetramethyl ammonium salt of this anion in formamide in the presence of a template such as octadecyl trimethyl ammonium bromide. And then these anions here will aggregate in the periphery of these micelles. Okay, what you can then do in the next step is to add a transition metal ion, for instance, copper 2 plus, nickel 2 plus, zinc 2 plus, or cobalt 2 plus. And then these ions can actually coordinate to these terminal sulfide units and link these germanium sulfide clusters together in the periphery of the micelle. And then you obtain what is called a mesostructured metal germanium sulfide. Okay, so in this case, you can actually not remove the template by calcination or extraction. If you try to do that, then your mesostructure will collapse. So this indicates that in this case, the linkages provided by the transition metal ions here are actually not strong enough so that the template can be removed. So this is a general problem in the preparation of mesoporous materials. The framework in itself has to be interconnected via quite strong and many bonds so that it doesn't collapse upon template removal. And this is actually an example in which this does not work. Okay, so another extension of this concept is the preparation of mesostructured Prussian Blue. You've probably heard of Prussian Blue. Prussian Blue is known since the antique, and it was actually the first modern synthetic pigment also. So Prussian Blue is the iron 3 salt of potassium hexaferranous cyanate 2. So you see here the hexacyanoferrate 2 ion. Okay, so because the ion here has a 2 plus charge, the complex ion is a 4 minus charge. Okay, and if you add, well, iron 3 plus to a solution of that hexacyanoferrate, for instance, potassium hexacyanoferrate, then Prussian Blue drops out of the solution. So essentially, the Prussian Blue, the iron 3 plus coordinates to the nitrogen atoms here and interlinks the hexacyanoferrate ions together. And you see here the final structure that results. So this is a cubic structure, okay, in which the iron 2 plus anions, iron 2 plus species are coordinated all by carbon, okay, and the iron 3 plus species, as you see here, are all coordinated octahedrally also by nitrogen. Okay, now how can you make a mesostructured form of Prussian Blue? So here's how. You can, in this case, use a modified structure directing agent, a modified template, which is here an alkyl group, okay, bound here to this quaternary nitrogen, which is formerly the negative charge. Okay, but this nitrogen is part of a pyrazine ring, which has an additional nitrogen here. Okay, so now you can actually react this surfactant molecule with this species here. Okay, that's sodium pentase cyanoamine ferrate. All right. And then during the reaction, this amine ligand here is lost, and the iron actually binds to that second nitrogen here at our surfactant. Okay, so now you have actually a surfactant which has this complex ion head group here. Okay, so now again in a formamide solution, this surfactant here forms micelles, and when you add iron 3 plus to this solution, then that iron 3 plus will interlink the surfactant head groups to form a Prussian blue, okay, which is actually indicated here. Okay, and the Prussian blue will actually form around the micellar template. Okay, this way you have prepared a mesostructured Prussian blue. So again, this prep doesn't allow for the template removal. The template is in this case still anchored to the pore walls, Prussian blue pore walls, via coordinative bond, and the Prussian blue framework itself is actually too weak in order to withstand the removal of the template, for instance, by combustion. Solvent extraction in this case also doesn't work because we have here a covalent dative bond between the nitrogen of the surfactant and the iron here in the Prussian blue. All right. Now, another pathway to mesoporous materials, which are non-oxidic, is a process which is called nanocasting. And in nanocasting, you avoid solution assembly altogether. So rather than that, you use a periodic mesoporous material as a so-called hard template, and you infiltrate your mesoporous material with a precursor of your target material, and then you convert that precursor inside of these pores into your target material, and in the last step, you remove the hard template, so that your produced mesoporous material is the inverse of your original material. So for instance, you can also produce mesoporous carbons this route. So for instance, you can start out with an SBA 15 material. Okay, this is nothing else but a periodic mesoporous silica material, which has been templated by a block copolyether. And you infiltrate this SBA 15 using a sucrose solution, okay, whereby the sucrose, in this case, acts as a precursor for carbon. Okay, so once your sucrose is infiltrated as an aqueous solution into the pores, you can just heat this composite material, and then your sucrose will carbonize. That's the thermal property of sucrose. And you will have your pores filled with carbon. You may actually have to do this process more than one time in order to fill the silica pores completely with the carbon. Okay, so now remember that a material like SBA 15 has also little micropores in between the mesopores. Therefore, these mesopores are actually interconnected via little micropores that are also filled with carbon. Okay, and because of this reason, when you now etch away your silica pore walls with, for instance, hydrofluoric acid, you do not get individual carbon nanorods, but you're actually getting periodic mesoporous carbon framework in which these nanorods are actually interconnected via carbon fragments that have infiltrated the micropores. Okay, and your periodic structure, periodic mesostructure is actually retained. Okay, so now if you want to, you can even use this produced material as a starting compound again and to do the reverse process. So you can infiltrate now this carbon material with, for instance, tetraethoxysilane. You polymerize this tetraethoxysilane to form silica, and then you remove the carbon part by in air, oxidize it in air, and that leaves you then the periodic mesoporous silica behind. Okay, so this way you actually have produced the structure that you have started with again. Okay, of course, from a practical standpoint, there is no point to make the same structure again from the original structure. This is just basically an exercise in order to show that the reversal also works, that we can also start from a period of carbon and produce a mesoporous oxide, in this case silicon dioxide, using that periodic mesoporous carbon. So you demonstrate the functionality that a mesoporous carbon can also be used as a template. Okay, so there are interesting variations for that. You can actually also make carbon nanotubes that are interconnected into a periodic mesoporous structure. So when you choose your reaction conditions so that you do not fill your SPA15 pores completely with carbon, but you actually only add a layer of carbon on the pore surfaces, okay, leaving actually hollow tubes, then after the template removal, you get a material with a bimodal pore system, which is called the CMK5. Okay, so you still have these cylindrical mesopores, okay, that are straight in your carbon structure, but you also have pore space in between these, well, cylindrical mesopores, because the cylindrical mesopores are interacted by little rods due to the presence of the microporosity in the SPA15 template. Okay, so you see here how you can actually characterize material like this. So a typical characterization would include small angle X-ray diffraction. Okay, you see here actually the peaks at relatively small 2 theta degree angles between approximately 0.5 and 3 degrees to theta due to the large structure. And you see here actually the peaks that indicate the periodicity of the mesopores. Yeah. You see here complementary transmission electron microscopy images, which actually show the tubular structure of the material. So you see here the large tubes, okay, but you still see that these tubes are arranged in a periodic pattern, and that's only possible because the tubes are actually interconnected. Okay, you see here high resolution electron microscopy image of the same. You see here a central pore, which is actually surrounded hexagonally by 6 other pores. Okay, so you can see that bimodal pore size distribution. Also, when you do take a nitrogen adsorption isotherm and analyze the pore sizes from that isotherm, see here actually the pore size distribution as a function of the pore size, and as you would expect, you have a bimodal pore size distribution indicated by these 2 peaks here. So the larger pores here are associated with they're actually associated with the pore space in between these tubes, and the small pore sizes here are associated with the diameter of the internal diameter of the tubes themselves. All right, so you can extend this hard templating concept also from mesoporous materials to microporous materials, for instance, zeolite. So you can, for instance, also use a zeolite, in particular a large pore zeolite, then it's easier, as a hard template. So we've discussed previously zeolite Y, which is a large pore zeolite with pore entrance of 0.74 nanometers and an effective pore size of 1.3 nanometers. So these pores and pore entrances are large enough in order to make carbon precursors, to allow carbon precursors to enter. So in addition to sugars like sucrose, you can, for instance, also use furferal alcohol, a molecule is shown here. This is also a relatively small molecule, and as an advantage over sucrose, it's actually a liquid. So it has actually a melting point of minus 29 degrees Celsius. So you do not have to infiltrate an aqueous solution of your precursor, okay, which has the disadvantage that your solvent actually also consumes space, which you don't want because you want to fill your pore space effectively, as effectively as possible with your precursor. So furfural has the advantage that it's a liquid in itself, so you can just infiltrate it as a liquid and then polymerize it, acid catalyzed at a higher temperature, and then this respective polymer further carbonizes. Okay, so this way you can produce a carbon material within the pores of a zeolite. Okay, now because the pores are three-dimensional pores are interconnected, that carbon framework that forms in that pores is also a three-dimensional framework, which is interconnected. Okay, and so that after you remove the zeolite material, that can be again done by HF, we can produce a periodic microporous carbon now, also called zeolite templated carbon, which has the inverse structure as the zeolite itself. All right, you can also extend the idea of infiltrating a pure liquid to the preparation of nitrides, such as mesoporous nitrides. So for instance, you can melt infiltrate hexachlorotriphosphosine into periodic mesoporous silicas, and then polymerize that hexachlorotriphosphosine to form phosphorus nitride. So this way you have produced a periodic silica phosphorus nitride mesocomposite, and then you can again remove the template using a suitable etching agent. So in this case, the template removal is more difficult because the phosphorus nitride material reacts similarly than silicon dioxide itself, yeah? As opposed to carbon, which has very different chemical properties in comparison to silicon dioxide. So you have to etch very carefully, in this case with a mixture of HF and acetone, in order to remove the silica so effectively, and then you actually have a periodic mesoporous phosphorus nitrogen framework. All right, then our time is over, so let's stop at this point.